Sure. But I guess this thing is just going to work now. Yes, sure. Yeah. Oh. Sure. Oh. How long should I talk?
It's 1 hour.
The whole slot.
Yeah.
Yeah. Okay.
And
yeah, there's flexibility in the end.
Yes.
Yeah.
Welcome everyone to the weekly seminar. Today we have Reinhard from Beirut University in Germany. And he's going to talk about graph databases, in particular finding paths in graphs that are simple or trace or this kind of things.
Yep.
So just before we start, I remind you that if you want to ask a question, to grab the queue first, because people on Zoom can hear us. This is a microphone.
Okay.
Sorry?
You see it, yeah. Yeah, it seems to be working. Okay, so yeah, thank you very much for the introduction. And so this talk is going to be about one of these cases where, yeah, one of these problems that I guess kind of understood if you don't have graphs with label information. I mean, we know how to find shortest paths. We know how to find simple paths in many of these problems. We even have a fine-grained complexity understanding. But once you start adding labels on your edges, and once you want to start understanding which kind of labeled paths you can find easily or not easily, yeah, the situation can change quite a lot. Okay, so let's first give you an idea of where these problems are coming from. So Michael already said it. It's coming from graph databases. So in graph query languages, you can ask things like this query that you see here on the left, right? You can say, okay, I want to match something in my graph. This blob here, this is your graph database, okay? And you can say, okay, I can match P, and P is going to be a path. And now what are we seeing here? P should go from X to Y, so from some node X to some node Y. And here I'm putting some condition on this node X. I mean, with this, I just want to say, I want to go from this node S here, from this concrete node S to this concrete node T. So this is up to now, we just have S to T reachability in your graph, right? And here you have an additional constraint on the path that you want to have from S to T. And this constraint in the syntax of that language, this is just saying at the moment, every edge on this path S should be labeled with an A, okay? So this is just in a graph database query, the problem, find all the paths P from this node S to this node T in your graph that only use A labels, okay? So that's what's going on here. Now, in the real world, these graph databases, I mean, I've drawn some arrows here, yeah, to symbolize that this path is supposed to be a directed path. But in graph databases nowadays, especially in particular in the property graph data model, you can have directed edges in your graph, but you can also have undirected edges. Like for instance, if two people are married, then the married to relation is typically a symmetric relation. So you could model this with undirected edges. Okay. And then, yeah, this thingy here that says, okay, every edge needs to be labeled with an A. Well, in graph database query languages, you can use arbitrary regular expressions here. And then you're asking, is there a path from S to T such that, well, if I take the sequence of labels on this path, such that this sequence forms a word in this regular expression. Okay, so that's what you're asking then. And actually, you can even in these you can even use two-way navigations. And in one expression, you can use two-way navigation and both directed and undirected edges. So you can say things like, okay, I want to follow a couple of A edges forward, then a couple of B edges backward, and then something symmetric. And you can do all this kind of stuff. So this is really, really general. Okay, and another thing that you're seeing on this picture already is that, well, if you ever want to return all these paths P that do this, well, here you're going to have to return infinitely many paths because there is a loop here and you can follow this loop as often as you want. Yeah? And because of this, these query languages also have other ways to restrain the number of paths that you're interested in. So you can add the word simple here, which means, okay, now I only want to compute all the paths without repetitions of nodes, okay? So no loops. You can also say trail, which means no duplicate edges, and you can say shortest, which means that it doesn't mean that you're only interested in the shortest paths between S and T. It means that you're going to consider all the paths that match your expression, and then of this set of paths, you're only going to return the shortest paths, okay? Right. And then the difference between trail and simple, yeah, just a few words about this. So the thing that I've drawn here, well, if this thing is just a node and this thing is also just a node, then the path that you're seeing here is actually a trail, right? So a trail can visit nodes twice as long as you're not going through the same edge twice, it's fine. Okay, yes. Yes, get the cube.
Yeah, so I'm trying to understand if you say you can specify the direction to follow the edge. I'm trying to understand if that adds expressiveness. So why can't you just say for each label, you say A left and A right, and then can you express direction?
You could massage the problem like that. Yeah, if you want to study like the fundamental, wait a minute. Okay, actually, I would have to think a little bit about this.
Okay.
Let's see. Yeah, let's discuss this offline because Yeah, okay. All right, so these are a bunch of things that you can say in this language, and this motivates a whole bunch of problems. And to motivate even more problems, if you want to understand this kind of queries, then, well, the things that you return, these are also, you have many options here, right? You could return just the x and the y, only the endpoints, x and y, such that there exists such a path. Here, everything is fine, and actually you don't need to care about loops because there can only be like quadratically many such endpoints in your graph, right? So this is fine. Your output is always going to be at least finite. But of course, once you can write something like this, now I want to return the actual paths. Well, your whole problem from a fundamental point of view is really changing because now, yeah, to study this from a theoretical point of view, it starts making sense to consider questions like, okay, let's try to enumerate all the paths. Are there delays that I can guarantee, and so on and so forth. Yeah, so there are like many problems you can study. Yes, the cube. Yeah.
So can I also give 3 points as t and something in the middle, let's say? And like the question is like, does this middle point belong on the paths from S to T? Satisfying regular.
Yeah, you can also add things like this in the language. Yeah, you can ask things like this. And in the general language, you can write patterns like this and then separate them by comma, and so it's like conjunctive queries built out of atoms like this, right? So you can do that in the general language, but okay, that's not the thing that I'm focusing on today, because if I would add that as well, the problem is just too big for a 1 hour talk. Yeah, but you can do things like that. Okay, right? Yeah, and now what we want to look at is, now you have this kind of queries, and now you want to understand which kind of queries of this form, and okay, we're only going to consider one-way navigation, can be solved efficiently and which one cannot be solved efficiently. Yeah, and this gives rise to a number of problems that seem fundamental. So let's have a quick look at that. And for this talk, I'm only going to talk about decision problems. We looked at enumeration versions of the problems as well, but I'm not going to talk about that today. Okay, so decision problems motivated by this setting. Well, first question is, okay, this is just in directed graphs. You want to find if there is a path that matches some regular expression E. Yeah, so the regular expression E is always fixed. So we're considering data complexity here for the database people. Okay, so this is actually an infinite number of problems, yeah, that I'm talking about. For every fixed E, this is like a problem. The input is always an edge labeled directed graph G, and then you have a start node and a target node. And the question is there a source to target path in the graph that matches your expression E? Fine. Actually, if you're only interested in decision problems, then this is, I mean, this question answers, is there an arbitrary path that matches E? And this, of course, means the same, is there a shortest path that matches E? So this is the same problem. Okay, and then you can ask the same question for simple paths and for trails. Okay, and you can now you can try to understand for which expressions E can you solve these problems efficiently, and for which expressions E is this problem, let's say, NP complete. And then you can look at the same problems in the undirected world. Okay, so this is a whole bunch of problems. First remark, if you're just interested in, is there some path that matches a fixed expression E, then these problems are always easy as well in the directed case as well as in the undirected case. Essentially, you can solve it. I mean, if you're a bit familiar with the automata tools that you can use here, you can turn your expression E into a non-deterministic finite automaton. You can take the product of E and then your graph, where you take the start node as a start state and the final node as a final state, and then you build the product and you test intersection emptiness. This is a construction that gives you this complexity. So this is fine. This is all tractable. People have looked at fine-grained complexity of this in an ICDT paper, and yeah, this is also optimal in a sense, actually. Okay, for simple path and for trail, this is less obvious. So now the question of this, whether this problem is tractable, it depends a lot on your expressions E. Yeah. Okay, and now the further part of the talk, I want to tell you three things essentially. First of all, in my abstract, I said, okay, for simple paths and for trails, the relatively well understood which expressions E give you tractability and which don't. And I want to give you just the main idea here and just the main idea here. When you go to the undirected world, it's all, we don't understand this so well. And there are many open problems here. And here I would like to give a couple of ideas. Yes?
Just a quick question about, so the longest path that you ever have to consider for these queries is like the permutation of any permutation of nodes, because you don't have to look at the loops ever, right?
For trails and for, okay, for simple paths, yes. For trails, you may be a little bit, it could be like the number of edges. Yeah.
But then it's like factor 2 or something.
Yeah. Exactly.
So there can't be more than all possible node permutations, essentially.
Yes. Yeah. But still, it's, I mean, we will see that in some cases for even very simple expressions, the problem can be NP hard, even if the expression is fixed.
Right.
Yeah.
Okay, thank you.
I may have missed this. So in the previous slide, it said size of expression as like for the easy case, like it was like bar E bar. What exactly does that mean?
Oh, okay. Size of the expression, we can take the number of alphabet symbols in the expression. Yeah, and actually for these problems, if you consider E not to be part of the input, then actually this is even a constant. But if you would take the expression E as an input and the graph, then size of the expression, it's like the number of alphabet symbols you have in the expression. Or if you would like to think in automata, you can think of the number of states of your automata. That's the measure you want here. Okay. Yes. Okay. So let's see where we go. Okay. So for in the directed case and simple paths, what's the main result there? This is by Bagan, Bonifati, and Gross in POTS 13, and then there was a journal version in 2020. And they showed that there is a dichotomy for these kind of problems. And depending on the expression E you plug in. And okay, they say that if this expression E is in some class that they call SP tract, like the tractable class for simple paths, then the problem is in P, and otherwise these problems are NP complete. Okay, now of course I should try to give you at least a little bit of intuition about what this means, this tractable class. Okay, so what kind of languages can you deal with here? So I'm just going to define a bunch of regular expressions here, by induction. So first of all, you say that a term is a regular expression of this form. So this is just, you have some word, W, or empty, okay? Or you can say this A here, this is just a set of symbols, okay? So you can have a set of symbols and then you want to have a length at least K, or again, you could skip this, okay? So that's what's a term for now, all right? And then you say that a sequence, this is a regular expression of this form. So you start with some word, W1, and then you have a whole bunch of terms, and then you end with some other fixed word, W2. Okay? So that's a sequence. And now they say that a regular expression is in the good class, the tractable class, if it is equivalent to a union or disjunction of these sequences. Okay, and that's the tractable class. And then the result is for every language that you can write like this, your simple pathfinding problem is tractable. And for every language that you cannot write like this, the problem is NP complete. Okay, and now I would like to give you like a bit of intuition about the proof idea, and then maybe a bit more intuition about the class. But Paris. Or actually, the mic is already with you.
Yeah. So the notation A to the plus greater than K. What is that?
It means Yes, sure. It means so if A is a set of symbols, and it's just okay, let's say just two symbols, right? Then this is the regular expression, just A plus B, right? You can match an A or a B. And then if I say at least K, it just means you have this A plus B a number of times, K times, and then after that, you have this expression, which means that you can see it as often as you want. It just means you want to see a symbol from the set A at least K times, yeah, and then it does. You don't care anymore. Okay.
That was exactly my question.
All right. Okay. Okay. All right. Okay. Good. Yeah. So that's the class. How am I doing on time? I could give you a bit of intuition about why these languages are tractable. Just very, very briefly. So why, if you have a problem where you want to find paths of this that match this, and your expression is fixed, what could you do in principle? But this is just a very high level idea. So if you have an expression that's essentially a concatenation of things like this, yeah, it means that, well, your path needs to start with some fixed word. Okay, you can brute force this, yeah, and you can also need to end with a fixed word. You can also brute force this. And then you have these parts in the middle where you either need to read a fixed word or you need to find a bunch of, yeah, a path of length at least K with some, yeah, with a fixed label constraint, yeah? So what does the algorithm do? Well, the algorithm just brute forces these parts, yeah? You just do a huge for loop where you fix these parts that you need to see, yeah? And then to connect these parts, you just do reachability, right? So this is the part where you're reading, you have seen K symbols from this set, and now you say, okay, now I just want to find some kind of path from here to here, right? You cannot remember all these nodes, but you do like an n-log space reachability test here, and then you just complete everything. And now, of course, you need to prove that when you find this, yeah, this can still have loops, and this is still illegal. Now you need to prove that when you find this and you cut away all the loops, you can turn this into something that still matches your expression here. Okay, this requires some non-trivial work, but this is like the very high level idea. Yes. Who is closest to the box? Yeah.
So what's the difference between yellow and blue?
Oh, I just wanted to use different colors to make, yeah, to illustrate that this one is going like this and this one is going like this. So yeah, that was my intention. It's not no deep meaning between difference between yellow and blue.
What do you mean by brute force?
By brute force, I mean your algorithm. So suppose that you need to start with AAA, okay? So then your algorithm would start with a loop of all paths that start with 3 A's from S, and you just keep these 3 nodes in memory. Yeah, you do that, and this is fine because your expression is fixed. Okay, and then when you do these parts, these reachability parts, you check that you are not using nodes that you have fixed in these red parts. Okay, that's what I mean. Yeah. Okay, but again, this is just meant to be like a very high level intuition. Okay. Oh, wait, should I skip this? What's the time? Yes.
The last slide.
Yeah.
To make it a simple path.
I am.
So in this slide, to make it a simple path, you need to modify the blue loop, not just cut it.
Yes. To make this one is okay. So to make this one a simple path, of course, you can cut away this, and then actually what you would do is you would follow this one, and then you continue here, which means that you have completely skipped this thing.
But you are not.
But this is all right because you have this plus epsilon there. That's the thing.
Okay.
Yeah. And you need these plus epsilons. If you don't have these plus epsilons, you can prove that the problem is hard. So the problem, this problem here, for example, is hard for, let's say, this expression here. Yeah, for A star, B, A star. This doesn't work.
But you miss the red part that.
Yes, but this is okay.
Okay.
This you can. It's okay to miss this red part because this means that you have a sub-expression like this, but then you use this epsilon.
I thought the red part was the WI from the sequence.
Yeah.
Okay.
Yes. So it's what you're checking with the red things is that in your algorithm, once you go in there, you want to see everything. This is what you're checking with the red things. And the second thing that you're checking with the red things is that if you do these intermediate reachability tests, you are not going through these red things because these are places, once you enter it, you're not allowed to cut there. That's the point. Yeah. Okay. Yeah.
So you said that in the yellow part, you can just cut the loop, but then the at least K could be violated, I guess?
No. The at least, yes. The deal with the at least K is here you want to check that you see the at least K. And then this yellow part, this is, okay, you have seen at least K in this block. And from then on, you're just going to do reachability. Yeah, yes. That's the rough idea. Okay. Yes.
It seems like, isn't it kind of trivial if you can allow epsilons everywhere?
If you can allow epsilons everywhere, then the problem is trivial.
Right.
So if the languages are, let's say, downward closed, if the languages are just closed under deleting single symbols everywhere, then of course this problem, finding simple paths from source to target, this is just the reachability problem. You can cut everywhere you want, right? But these languages are not closed under deleting symbols everywhere, right? And so in these red parts, I mean, what happens here, you could skip over an entire red part, this is fine, but you cannot, once you enter a red part, you cannot delete things in here, and that's the whole thing. And what this result is saying is that you can deal with paths like that, but, and yeah, you can deal with languages like that, and everything else becomes hard.
Okay. Oh, wait.
Yeah.
So you always need the same A in these things to glue together the path, or how
here,
does it
yes. Work? If you change your A here in this at least K, then also the problem becomes hard.
Okay.
Yeah. It's no. It's not. Sorry, this is not the same A across the whole expression, but inside one term, it needs to be the same A. Yeah. Yes.
Can you explain to us what property? So you have there W, or you have A to the power at least K.
Yeah.
What is the main property of this little snippet of a regular expression that you need in order to, why can't I use something else than W? Why can't I use, I don't know, A to the power exactly K? Or what other things could I try to use there, and why do only these work?
A to the power exactly K.
Let me put it differently. I could, instead of W, I could take, for example, W1 or W2, and then plus epsilon.
Oh, but then you're still equivalent to a disjunction of these things.
I see.
And the same holds for A to the power exactly K. Because then you can rewrite the expression in some normal form, and then you're still equivalent to a disjunction of these.
Okay.
Yeah.
So just kind of following up on your question. So here you are not taking into account how big your expression is, right?
Yes, exactly.
And that's why it's okay to brute force over anything and make a huge disjunction.
Yes, correct. So we also looked at these kind of problems where the expression is part of the input, But then we started to look at this from a parameterized complexity point of view, because of course you can, if your expression is arbitrary, you can encode the Hamiltonian path problem, of course, in this way you need to get a different approach. Yeah. We also looked at that, but that's not in this, it's not in this current talk. Yeah.
Maybe you'll talk about this in the next slides, but is this condition decidable?
This condition is p-space complete.
It's p-space complete.
Yeah, yeah. On an input expression. Yeah. Yes. Okay. Discussion is good, but I'm gonna skip a little bit of stuff now, and I think it was very good to have this discussion to give you just an idea of what these languages are like. This is okay. This is an equivalent characterization of this tractable class. Let's not digest it now. Let's skip this. Yeah. So this is just, I mean, we have discussed about these languages now. This is an example of a good language. Yeah, you have this at least K condition. You can skip entire blocks, so this is fine. But one interesting languages that is not okay, for example, is this one, right? This is not in the. This one is not in the good class. So even length, even finding even length paths in directed graph, even length simple paths. This is an NP complete problem. I can talk a bit more about that later as well.
What happens if I put here b equals to not greater than or equal to?
B equals to. Well, then doesn't this? But doesn't this rewrite to a disjunction of b equals to? I mean,
then you say it's a word.
Yeah, exactly. Then it's a word. Yeah. And then you rewrite it to a disjunction of these things. I think you can do that in that case. Yeah. Okay, fine. Let's move on a little bit, because actually my main storyline was going to be directed graphs are like fairly well understood. I did want to give you an intuition about the class, right? But the undirected case there, things are much less understood, and I would like to get to this a bit. Okay, so these were simple paths. There are trails as well. For trails, there is a similar dichotomy that says, okay, as long as your your language fulfills some condition, the problem is in P, and otherwise it's NP complete, right? For trails, we don't know a nice, let's say, syntactical condition on the expressions. In the previous case, I could just say, okay, a term is this, a sequence is this, and then your expression is equivalent to a union of blah, blah, blah. For the tractable class for trails, we don't know something like this, unfortunately. And okay, so this is why the situation there is a little bit more interesting. So I'm going to go quickly over trails now to get to the undirected graphs, which I think have some cool problems. Yeah, and just to give you an intuition about these tractable classes for simple paths and for trails, here is the class. The tractable class, if you're interested in simple paths. These DC here, these are the downward closed languages. So the language is closed under deletion of symbols. Yeah, so there is something in here which is not in here, and so on and so forth. And for trails, actually, the class is a bit bigger. The tractable class is a bit bigger than for simple paths, because well, you can do expressions like this. In simple paths, this would be hard because it's another version of the even length path problem. But for trails, well, a B edge can never be the same as an A edge, which makes this class easy, at least on labeled graphs in which every edge can have exactly one label. Okay, but this is just, so let's go over this and let's go to undirected. No, still a question?
One question about directed. Do we know anything about the complexity under P? Because, for example, its ability is in NL. So can we say,
yes.
Do we have P complete problems
yes.
or stuff like that?
Okay, so the dichotomy is actually a trichotomy, and it says, okay, you have hardness, NP completeness. The tractable class is actually NL complete, and then you have the finite languages that are in AC0. Okay. Yeah. Okay. That's what the result.
Everything that is in P is actually in NL.
Yes.
Okay.
Yeah. Yeah. Exactly. Yeah. That's what the result says. Yeah. Okay. So the undirected world looks a lot more like this. There are a lot more holes. Maybe I can argue it also looks a little bit like this. There are treasures to be found, maybe some battle to be fought. Yeah, once you get there, if we can completely characterize, if we would be able to get a similar characterization of this problem in the undirected case, yeah, we will definitely solve some nice problems here. So there is definitely some gold here. And actually, I just want to give you a bit of intuition about what's going on in the undirected world. So first, I would like to give you an idea about, well, what is so different between the directed and the undirected world? And these are two problems. So this is the k-disjoint path problem, and then the modulo k path problem. These are two problems that are very different in the undirected and the undirected world. So what are these problems like? So the k-disjoint path problem, you're given a graph G and then node pairs, right? And then the question is, are there pairwise disjoint paths from S1 to T1, and then so on and so forth, all the way from SK to TK? No labels involved, yeah? So this is just a standard classical graph problem. So that's one interesting problem. The other interesting problem is, okay, again, you're given graph G and then nodes S and T. And then, is there a simple path of length 0 modulo k from S to T? Yeah? All right. Now, why are these problems relevant to us? Well, the two disjoint paths problem is essentially the same problem as saying, I want to find a simple path from my source to target that's first labeled with a bunch of A's. This is your first simple, yeah, so this is your first node pair. You want to find that from S1 to T1. Now you could have in your reduction a single edge from your target 1 to your source number 2, which you label with a B, and then all the rest of your graph is labeled with A's, right? And then solving this problem essentially boils down to solving the two disjoint paths problem, okay? So that's why this problem is relevant. The other one, well, yeah, modulo k paths. Yeah, if you want to find paths that match this simple paths, yeah, then yeah, this is finding paths of even length, right? And of course, the more A's you insert here, yeah, this increases your K. So all these modulos are relevant for solving our problem. Yes.
So disjoint means not sharing nodes or not sharing edges.
Okay. For the purpose of this talk, let's say not sharing nodes. If you want to understand the whole picture for trails and simple paths, then you consider two versions of the problem. One is not sharing nodes, the other one is not sharing edges, and yeah. Yeah, but for the purpose, let's talk about node disjoint at the moment. Yeah, good question. Yeah, thanks. Okay, so why are these so different? Well, in the directed world, by a classical paper here, the two disjoint paths problem is NP complete. This is like there's a nice gadget in this paper, and it just does the job. Also, the modulo k paths problem is NP complete for all k, bless you, for all k bigger than 1. If you have time and energy later on, I will prove this in one slide from this one. It's a very easy proof. Okay. In the undirected world, the k disjoint paths problem is in n to the third, and this is in Robertson and Seymour's graph minors 13 paper. So yeah, that's what they do. And modulo 2 path, so this one here, this one is in polynomial time. If you have energy later on, I can again show you the proof in 3 pictures. And modulo 3 paths and the ones above that, I guess we don't know. Modulo 3, we definitely do not know. Okay? Right. So that's why this is very different. And once you start getting into these problems, you really get the feeling of this guy here on the wall. So you have tractability here. Okay, fine. We can handle these and these cases, but change a little bit detail here and there. Like, I don't know, attach one loose rock here and you fall into intractability, right? So that's the situation here. You're really on the edge here. I mean, yeah, fine. Okay. Yeah, we try to understand the undirected case, and we proved a number of things. What does this say? This is some kind of generalization in the undirected world of this. Okay, now let's start different. One thing we observed is, so you have this two disjoint paths problem that's tractable in the undirected world, but once you start adding labels to your paths, there are cases in which this problem becomes easy and in which case this problem becomes hard. If you say your first path needs to be labeled with A's and the second path needs to be labeled with B's, then the problem becomes hard. Yeah, and then this can be leveraged to get some kind of clear idea of expressions of this form. So you first follow a bunch of symbols from a first set, and then you read one additional symbol. So it's generalizing this case here. Yeah, so some of these cases become tractable on undirected graphs, yeah? And then you read some symbols in some second set. Okay, and we kind of understand that case. Let's go over the. Let's not do the details. Okay, and then here is another. This case I think is maybe a bit more interesting. So here we wanted to understand, to generalize this modulo thing, right? So let's say that W is a word, and if W has length at most 2, then we know if we want to find undirected simple paths of the form W star, so your paths need to match like a cyclic repetition of this word W. Yeah, so simple paths and trails, yeah, these you can find all of these in polynomial time. If your word has length at least 3 and it has at least 2 different symbols, then the problem is NP complete. Which means that in this case of repeating these cycles of words, we understand everything except the case where these words W have all the same letter. Yeah, which just boils down to modulo counting. Yeah, and this is so this is tricky, the modulo counting case. I mean, it's on the open problem board, so it's also not.
Something like ABA star.
ABA star is hard. Because then W has at least 2 different. There is an A in there and there is a B in there. Yeah, this is hard. Yeah. Okay. Fine. So now we are with some situation here where you guys came up with lots more questions than I thought, but I thought that in the at this point you would have like at least these kind of questions. So first of all, I know I've been talking about these simple paths of even length. Why is this hard in directed graphs? I can show you a proof in one slide. Why is this problem easy in undirected graphs? I can also give you a proof in one slide. Oh, we have seen that in the examples we've seen until now, we have seen problems that are hard in the directed world, and once you go to the undirected world, they become easy. Is this always the case? Okay, what's so intriguing about 0 modulo 3? And then a question I heard at several talks here at Simon's. Okay, apart from this thing, what are your easiest open cases? Yeah. Okay, and now I have like something like 5 slides on this, and we could discuss these questions. For the people who have to be somewhere urgently, we can say, I mean, you can escape. Yeah? If you don't want to go to details, it's fine. I will definitely not be offended. And then for people who want to hear a bit about this, I can just give you some intuition. Yes. Yes, the box.
So what if you assume some conditions on the graph?
Very good question. I have not looked at that at all. Yeah. Yes. Very good question. I have no idea. Yeah. Okay. So let me just quickly go over this. Okay. So why is finding simple even length paths hard on directed graphs? So we had this classical paper that shows that the 2 disjoint path problem is hard. And from this, you can prove very easily that finding paths of even length in directed graphs is hard. Why? Okay, suppose that this is like your input of your 2 disjoint paths problem. So the question is, do I have a pair of paths from S1 to T1 and then from S2 to T2 such that these paths don't intersect? Okay, so now let's reduce that to the modulo 2 problem. Well, how do you do that? First of all, every edge in your graph, you just turn into 2 edges, right? You add a node in the middle. which means that every path in your original graph now has even length. Okay? And now you add one edge from your first target to your second source, and then here at the end you add also one more edge. Yeah? And now there you have these two node disjoint paths, if and only if there is a path of even length from this node to this node. Okay? And this construction works for all modulos. Yeah, you can just attach a slightly longer path here and you're fine. Okay? So that's a very, very simple proof. Yes.
Should schedule basketball practice.
Yeah. So is this the original proof of hardness for the even case?
I don't know.
Because
I don't know if this is the original
very
proof.
difficult to find, right? Yeah. Okay.
Yeah, I don't know if this is the original proof. My PhD student told it to me. Yeah, I don't know where she dug it up. Yeah. But
I'm missing something. What prevents you from having a even path from S1 directly to 2 without going to 1?
oh, but if you do that, then you have an even length path here, and then with this extra edge, you have an odd length, right? You need to go through this one. I mean, this is just one edge. Here you always have even length, even length, even length, right? And here is your only edge that can change the parity, and then from then on you're in the wrong modulo, yeah. And here you have to change the parity again.
There is no other edge.
Exactly. There are no other single edges, right? This whole graph is constructed, yeah. Yes, exactly. In the end, you reduce this original question to the question: is there a path of even length from S1 to T prime 2? Yes. Yeah. Okay. So this is hard on directed graphs. Why is it easy on undirected graphs? Well, so here is an undirected graph. Okay, this is an easy one. And actually, oh yes, luckily there is a path of even length, a simple one. So what can you do here? Actually, this is a very nice argument. It's by Edmonds. It's not written down in Edmonds' paper. In the paper where I found it, it said personal communication, but they described the proof idea. So what do? So here is your graph. What you do is you make two copies of your graph. And in the one copy, so this is the copy that's this copy. In one copy, you delete your source node, and in the other copy, you delete your target node. Okay? And then you add these blue edges, which are between nodes that are the same in the two graphs. Okay? Is the construction all right up to now? And then Edmond said, well, this new graph in this, Edmond said there is a simple path of even length in this original graph from your source to target, if and only if there exists a perfect matching in this new graph. And why is that? Well, if there is a perfect matching here, then part of this matching will be things like this, right? You just match a node in your copy 1 to the same node in your copy 2, right? And then you have a bunch of other matchings that you need, other matches that you have. Well, then the argument is that if you take these edges, which map some node to some other node, like in the same level, if you take the concatenation of these edges, then you actually get a simple path. And that's the argument. Seeing why this works, it takes some sitting down, I guess, and convincing yourself, but this was the proof I could explain easiest in 3 pictures. There are other proofs of this as well, if you're not convinced by this argument. Okay? But you see, for example, that by deleting your node S from your second copy, you're going to need to match S with with something in the same graph, right? And now this node, well, now you cannot match this node with anything anymore, or this node here. You cannot match it with this one. So again, you're going to have to match it with something else. And if you stitch this argument together, you get a simple path from your source to your target.
And in the other direction, how do you construct the matching if you have a path of length?
I don't know. I don't know the correctness proof. Actually,
Okay.
I just wanted to show you the, yeah. Yeah. I would have to think a bit about that, yeah.
How do you concatenate? I can't see how you
Yes,
concatenate.
how you concatenate, yeah. Maybe my drawing skills were a bit messed up. So how do you concatenate? So here you go from S to this node, yes? And now you jump to the copy of this node in the other graph, which is this one, yes? And then this one also has a matching edge, right? So then you go here. And then again, you go to the copy. Now you're in graph in copy number 2. Now you jump back to copy number 1. And then you match this to somewhere in the same graph. And then you jump back to the other copy, and then you do this. I see. Okay.
You just project it, like
yeah. Yes. You just, yeah. You can also look at it like that. If I would have like some crazy animation skills, I could now say, let's move this square on top of this square. Then this edge disappears, right? And then you see exactly this this simple path. Yeah. Yes, Paris.
So is it? Can you prove some kind of equivalence that you can somehow need matching, or that's necessary, or at least as hard as matching?
Like like from a fine-grained complexity lower bound point of view.
Even from like is this problem in NL, for example, or something like that, right? Because using matching means that it does not give you something in NL, but also doesn't give you completeness. So
I don't know if this problem is in NL, but it is in linear time, if this helps you. This is what, that's not in this argument, but in general, you can solve this problem in linear time. Is this the same for matching? I actually don't know.
You can solve matching in linear time?
Okay, no, this problem, the even length, this problem, the simple even length path problem, you can solve this one in linear time.
But that means you don't need matching.
Yeah, exactly. Yeah. This was like the closest thing in my head that I thought could answer your question. Yeah.
Okay.
So that would mean indeed that you don't need this matching. There are other, but the other algorithms are more complicated.
Nice.
Yeah. All right. Okay. Is undirected easier than directed? For simple, so what does this result say? For simple paths, yes. Okay, good. For trails, no. There are languages such that directed trail is easy, but undirected trail is NP complete. And there are languages such that undirected trail is easy, and then directed is NP complete. So for trails, these two are incompatible. It's like a whole, you start to see the cheese, yeah? Like what's going on here. This is one example of a language here. So directed, it's easy. This is, for directed, this is, what is it? Directed. Right. Oh yeah, for directed trails, this is easy. Why? Because you can cut away loops without things getting hurt. If you would have like a trail that matches ABC star, and you would cut out this loop, then due to the special labeling, you still have a path that is labeled ABC star. This argument works in the directed world, but not in the undirected world. So here you have the same in undirected. Here you have something, some path that matches ABC star, but if you cut away the loops, you don't get a trail that matches ABC star. Okay, and the intuitive reason is that when you were searching for your path using your NL procedure or whatever, you used some kind of edge in two different directions, and this messes things up. Okay, and then this other one we already kind of knew. This is easy in the undirected world. It's the two disjoint paths problem. Yeah, it comes from the graph miner work, but this is hard in the directed world. Yes.
Thanks. So I didn't understand the second example. So you are saying that you can use B in both in different directions? No. Yeah.
Okay. So why is this problem easy in the directed world? Actually, you can just use reachability with this expression and don't care about the trail condition.
Yeah.
That's what you can do here. Yeah. But here this doesn't work in the undirected world, because here actually there is a path from S to T that's labeled with A, B, C star. There is a path, but no trail. So here these two problems are not equivalent, and here these two problems are equivalent. Yeah, that's the argument. Okay. Good. Modulo 3. Yeah, this one. Why is this interesting? Well, we know a bunch of things about modulo 3, and then it seems like this problem should be in P, but we don't know how to prove it. Anyway, so what do we know about modulo 3? Yes, especially for this seminar, we have to talk about the triangle query. The triangle query has length 0 modulo 3, which makes like half of the people here immediately interested. Okay, we know what do we know? In the directed case, finding paths of length 0 modulo k, this is NP complete for all the k, so that's what we know. We know undirected simple path 0 modulo 2, this is in linear time. This is not by the argument that I showed, but by another paper that's going to appear on the slide very soon. And we also know that finding undirected simple paths of length different from 0 modulo k, this is also in linear time for all the k, which seems to bring us very close to this point where you can do this in polynomial time, right? But we still have no way to do it. So, okay, this is from this paper. What's actually happening here is these people have shown a linear time algorithm to detect if for a fixed number k, if all the paths from some source to a target have the same modulo. And with that, you can solve this, and also this, by the way. Yeah. But if there are path lengths of length different from 0 modulo k, we don't know a way to determine which of the modulos are the ones.
But what do you do about the 0 then? Or you just take one?
Yeah. You can figure out that the modulos are all the same. Yeah. And then if you get an answer no, then you know, fine. There is something of length different from 0 modulo k.
If it says yes, you just take one path and check.
Yeah, yes, yeah, yes, yeah. Yeah.
So this is not the same as saying, so 1 modulo 2 is also, one modulo 3 and 2 modulo 3, we also don't know. It is 1 or 2 modulo 3 that we know. Okay.
Precisely.
Okay.
We know 1 or 2, and yeah, exactly.
Okay.
Yeah.
So, but the
yes.
individual not.
So that's where we are since 1991. This paper is not trivial. Yeah, it's technical with bi-connected components and paths going into components and yeah. Okay, open cases. What are your easiest open problems? Okay, fine. Okay, we know that on undirected graphs, you can do things like this. So finding paths that start with a bunch of A's, then at least k B's, and then again a bunch of A's. You can do that, but this is by a non-trivial argument, because these A's here, they can intersect with your path here in the middle in weird places, and you have to do some work to make it work. It can be extended to actually to cases where for languages like this. So you can add a B star at the end, but what we don't know, for example, if now you want to also see at least one A here, we have no idea. Our whole construction is kind of brittle and it breaks down there. Okay, and that's like one of our easiest open languages. Okay, fine. Oh, by the way, I heard that COVID is coming back. Let's be careful. Okay, that's everything I wanted to say. Thank you for being here. Yeah, we can still discuss if you want. Thanks.
So I know some people who are planning to implement a graph query language. What is your advice for them?
So, okay, what's if you're going to implement this and you want to
see, the problem is different when you want to implement a query language because you want to not consider every case.
Yeah, no, I know. So if you want to implement this, then my advice would be first focus on the very simple cases where your expressions are just something like A star. Okay, and you don't have concatenations under the star, for example. Just focus on those queries first, because we have had a look at a whole bunch of queries that came from practice. We got like our hands on 800 million queries. And if you look at the regular path queries in there, it is very rare to see it. This was like on Wikidata, to see a concatenation under the star. So if you would optimize on that case, you don't have to deal with these hardness problems here. You can just greedily search for paths actually, but then you would have to focus on enumerating the simple paths and the trails efficiently. Yeah, but then focus on those languages. This is what people ask like 95% of the time.
Right.
Yeah, that's my advice.
Follow-up question, may I?
Yeah.
What do you recommend they should give as warnings to the users who sit down totally innocently writing queries and they submit the query to the system?
This again depends a little bit. I don't know if you want to flood users with warnings all the time. So you have to be a bit careful about that. So even, okay, I don't know, this is what you want to do with your system, right? You could give a warning, you say, okay, careful, this is a dangerous language.
You could give a warning, I'm going to implement this by brute force. I hope you have enough time to wait for the result.
Well, okay. In reality, of course, what is going to happen, even if you implement this with brute force, I think that quite often in the real world, your graph is actually going to have a special structure that could make your brute force approach also kind of feasible. If people ask for paths of the form, I don't know, you want to follow an A edge, and then you want to follow a B edge, and then repetitions of that. In the cases that we have seen in practice where people ask queries like this, actually the graph did not look like this, where you had this. You didn't have cycles that immediately cut between this middle node, and this means that again you could use your algorithm for A star greedily on these kind of expressions. But of course, this is now something that will depend both on your query and your data, right?
So then you are suggesting also another line of research, which is to characterize the classes of graphs. Perhaps there are simple classes of graphs for which any regular query is. Do we know anything about that?
Haven't started looking into this yet. Yeah.
Okay.
And just to say, the bounded truth graphs, I guess, would be such a class. I imagine unbounded truth graphs, all of this is tractable, right?
Okay, I guess so. But I'm not sure if graphs in graph databases have such bounded tree width.
Probably not.
Unless if you know that it's, I know, like a family tree, then I guess
well,
fine, but
even then in some cases.
Yeah, I know, but chance of cycles is reduced, right? Yeah.
You didn't say anything about the size of the alphabets, so it doesn't matter.
Well, if E is fixed, if your expression is fixed, then it's a constant. Yeah. But this hardness, I mean, where we saw this hardness, it was always with small alphabets. Yeah.
So what is acceptable performance in practice? So for large graphs, can anyone even afford quadratic, or do you always just want linear?
I hear people implementing real databases say that to n square, right? So they so that's what people seem to be aiming for. Try to be sub quadratic. I guess you can use some more expensive algorithms if you know that it's only going to be used on a small part of your graph, right? But then this leads to, I don't know, you need to do some cardinality estimation, and then you're entering a whole lot of other very tough problems. Yeah. But I'm just doing this stuff. Yeah, I'm not implementing this. I don't know very much about it. Yeah. About that.
So the first theorem that you mentioned was like your dichotomy showing that if an expression doesn't have this form, then it's hard.
Yes.
That seems like how do you go about proving something like that? Like if it doesn't fall into this thing, then it's hard. Is it?
Yeah. Okay. I didn't show you the proof, but actually you just show that if these expressions are not okay, like on a very high level, in a very high level idea, what happened in that paper, I think they said that okay, if the expressions don't have this form, there is just something that you can exploit to do. I think it's even one reduction from the path via a node problem, that you can force your expression to be at some point in the graph intermediately, and then for all these expressions you just have a construction that works. Yeah. But the paper itself, it spends a lot of time on trying to understand these languages, proving properties about these languages, and then at some point you figure out what you can exploit. Yeah. So this is the non-trivial part. Yeah.
Can you show your last slides about the open problem set? The last two examples or something. Right. Okay. So for example, the last one, we don't know about those two. So those two can be written as, like greater than equal to 2, like B star and A star, right? Then that just becomes a trivial regular expression. And it can be done.
Wait, I didn't get that.
Can the last one, B greater than equal to 2 be written as B star?
Yes.
And A as A star. So that's just a simple regular expression that can be done in linear time.
No.
Sorry?
No. If you're interested in finding arbitrary paths, yes, this is. I mean, the difficulty is not difficulty does not come from the fact that we write this with the number 2 or something like that, because this language is fixed. Anyway. We just use that as a notation to simplify how the expression looks like. But so yeah, the regular expression is just this one, right? A star, B star, and then A star, and then B star. So if you will, this is a language for which we don't know if you want to find simple paths in undirected graphs, if it can be done efficiently or not. In directed graphs, this is a hard expression. Yeah.
Okay.
Yeah.
So why is the insistence on simple paths in all the examples?
Why are we looking at simple paths in all the examples? Because shortest paths are easy. All of these can be done in polynomial time.
Okay.
This was like the problem that was solved on slide 1, and then you have everything else. Then you have these other things that these query languages can ask, and there it's much harder to understand what you can solve efficiently and what not. Yeah. So shortest paths and arbitrary paths, this is actually easy. Yeah.
But something important is that in practice, the query language asks for a simple path. Like
Exactly.
Cypher, which is the main route database, uses simple tries.
Trail, actually. Yes. Yeah.
In practice, they are used.
Yeah. You want the box?
Yeah,
The
here.
box, yeah.
Yeah, I don't remember. Did we have examples of intractable languages on undirected graphs?
Intractable on undirected graphs. Yes. Wait. Oh yeah. Yes, we can prove. Okay, I think I didn't write the theorem. Wait, no, actually yes. So this one. This is a hard one on undirected graphs. But it's easy on directed graphs.
So this was on the slide with the incomparability.
Yeah. So these cycle languages, right? If you have length at least 3, and if your word has at least 2 different symbols.
Yeah. So can I imagine this as I have a directed graph and I code it with ABC paths that are undirected and basically forces a direction?
Yes.
Okay.
With the A, B, and the C, you can force some direction somewhere. That's part of the proof. Yeah.
Interesting.
Yeah. Okay. Thank you.
This is something that, but when you showed that example where, this claim that basically if you have a trail, you also have a path, right? That was for the directed ones, that was true, but not for the undirected. Yeah, this context.